Thanks for being here. Thanks, PyData, for having me. Very excited to give this talk. Before I give this talk, I want to just mention that right now in the other room there's a cookie cutter talk. Cookie cutter is like a little tool which generates your scaffolding for your app, and there's also a data science cookie cutter template. Data science cookie cutter template, and that is very handy to start your project and have reproducible research or data science project. And I would just encourage you to check out this data science cookie cutter template. It's awesome. Okay, my talk. Gamification of search on Bandits and swipes. This is a talk I submitted, or the title I submitted. But while preparing the talk, I kind of came up with this spiritual title, which better describes what's really happening here. And it's about active learning, or how I learned to stop worrying and love small data. Show of hands, who knows active learning here? And I'm talking about machine learning active learning, not active learning in the sense that I'm cramming for an exam or something. Yeah? Okay, a few people. Good. I'm Stefan Otte, I'm on GitHub, I'm S-Otte on GitHub. I've been doing data science, machine learning stuff for quite a while. And before that, I was a roboticist, and I actually used active learning to create smart behaviors of robots, whatever that means. And now I'm data scientist at the Unbelievable Machine Company. We do everything related to data science, data engineering, ops, consultant stuff. So if you have problems, you can contact us. And of course, we're hiring, right? It's mandatory to say, I guess. Gamification of search. So, and in this context, we are talking about search in the car context. And we use search all the time, right? And quite often you have those little fields, you put in some information, and then your search space is narrowed down to a little subset, and you add some more information, and you narrow down your search area, narrow down, and hopefully, in this little subset, there are the cars that are really of interest to you, right? But there are a few problems. For one, if you do it on a mobile phone, it's really annoying to do it, right? Typing on a mobile phone and stuff and moving sliders, that's not a lot of fun. And also, a more fundamental problem is that maybe in this big black space, there's really the car that is that you're interested in. Search is not that black and white, I think. It's more like a degree, like a shade of gray, maybe. So, and we know, there are better and more fun ways of searching. People in different fields use it. Something is shown to you, and then you swipe, or you like it, or I don't like it. People like the swiping thing. They swipe and swipe. They swipe all day. They can't stop swiping, right? You know what I'm talking about, right? Yeah. I'm talking about this great app that we developed to search for cars, which is similar to this other unnamed app, right? And this is a fun, intuitive interface. And I could tell you how we did it and stuff, and that would be okay. But I think there's something more here. And we all know there's nothing quite so practical as a good theory. So I'm going to talk about theory here mostly. And more specifically, I'm going to talk about active learning theory. So, active learning. What is active learning? I'm quoting here. The key idea behind active learning is that a machine learning algorithm can achieve greater accuracy with fewer training labels if it is allowed to choose the data from which it learns. And I continue. An active learner may pose queries, usually in the form of unlabeled data instances, to be labeled by an oracle, e.g. a human annotator. And finally, active learning is well motivated in many modern machine learning problems where unlabeled data may be abundant or easily obtained, but labels are difficult, time-consuming, or expensive to obtain. This is the abstract from the active learning survey by Burr Settles. And that is It's a nice little book. It's like 70 pages, and it gives you like a very nice introduction to active learning. You can just read it on a weekend. It's really understandable, I think. And I'm showing this because it's like a great book, but also the guy who wrote it. Oh, you can barely see it, right? The guy with the brown shirt and the support vector machines. That's Sir Burr Settles. I always mix it up, sorry. This is a G20 demonstration a few years ago, and this is a Carnegie Mellon machine learning department, I think. They're all there. They have like signs like support vector machines, Bayesian against discrimination. I really like that one. Free variables, and the green one here is also pretty funny. Map reuse, map reduce, map recycle. That's a good one. Okay, but active learning, right? What is active learning really about? I read you this abstract, and the abstract really summarizes it quite well. And I think the essence of active learning are these 2 points. Greater accuracy with fewer training labels, and actively querying for data, or labels for a given data point. And this greater accuracy with fewer training labels, I mean, data science is all about data, right? And I think active learning kind of gives you good data. You don't get a lot of data, but the data you get can be very good. And with like little data, you can achieve or train good models. And then the second point is that by actively querying for data, we completely change this problem. Like all of a sudden, we have a sequential decision-making problem. So it's quite different than what we normally do in machine learning or data science. To bring that point home, like this is a supervised setting. We have our data X, and we have our labels Y. For example, cat, dog, whatever. But now in a active learning setting, we don't necessarily have labels. This is not strictly speaking an unsupervised problem, but we have to decide where we want to get data, where we have to query, right? So the question is, what is an interesting point? What is interesting? And there are many possible answers. So let's look at some data. Here's a little data set, and we already have 2 labels, right? Typical classification task. Here's a decision boundary. So what is interesting? We have many ways to decide it. We could say like maybe it's a distance of the points to the decision boundary, right? That is one way. So maybe everything in the darker area is interesting. Or maybe we use a special model. Let's say we use a support vector machine, right? The only real points that are of interest to us are potential support vectors, because only they influence our cost function, right? So everything in this, can you see my mouse? Yeah, everything in between the decision boundary there, that is of interest, basically. Or maybe we have something else. We have an ensemble of models that make the decision. So we have like 2 decision boundaries here, and maybe the disagreement between the two models. That is our interestingness criterion. So the little data point at the bottom might be of interest. Or let's do something completely different. Maybe we're interested in like something like the biggest model change, right? So let's assume we query this one, and this is red, right? So our decision boundary would change completely. So maybe that's an interesting point, right? Or we have something like a Gaussian process, and we use the uncertainty of our decision boundary there as a criterion for decision. So what is interesting? Quite a lot of these are interesting. They are, broadly speaking, and you should look at the active learning book if you want to know more, but uncertainty in general is interesting. Query by committee is very interesting. There are lots of expected somethings, like expected model change, expected error reduction, expected variance reduction, etc. And it really depends on your domain, on the model you're using, on runtime performance, etc. But you have a zoo and you can choose from it, basically. If you saw the keynote today, I think active learning is also used in some areas of the MLP world. At least the Burr Settles uses it in this context, and it's quite interesting. I mean, I showed like this little example of classification, but you can do arbitrary things with it. So, for example, I used active learning to make this robot in the world explore the world. And it had a model of the world, a probabilistic model, and it wanted to know like a lot of things about the world. So it like poked at stuff and gained some information, some knowledge. And the transparency here of the objects basically shows you how interesting they are. So the robot already explored the world a little bit, and then it updates the belief and keeps exploring, basically. So it's also active learning, but yeah, not just a classification task, right? And we used that to create the behavior of the robot. Okay, theory. There was, I think, human understandable theory. Let's get back to the topic, to gamification of search. We have our search space, but it should be more like a shade of gray, I said, right? So when we like swipe a car, we get some information about all the cars, basically. And as we get more information, we update our belief, right? Works. And it's also beautiful because if we get new information, we suddenly, the space that we already discarded is like searchable again. So maybe in the beginning I said, oh, I don't like this car, but I said it because the car was yellow and I don't like yellow cars, but then I gave some more information and all of a sudden these two cars in the red box, they are like of interest again, right? Maybe there's something like active learning or something similar that we can use. I don't know, maybe? And indeed there is, you know, as almost as I planned this talk, right? So there is something called multi-armed bandits. You're kind of familiar with A/B test? Who's familiar with A/B testing? Show of hands. Yeah, okay. And who is familiar with A/B testing and bandit theory? Oh, more than I thought. That's nice. Okay, in a multi-armed bandit scenario, you have a row of like these slot machines, basically. And normally it's called one-armed bandits, but here they call it multi-armed bandits. And you have to pull the arms, basically, and get money. And then the goal is to get as much money as possible, broadly speaking. So the problem statement is something like this, and I'm not joking, basically. Find multi-armed bandits. Step 2, play multi-armed bandits using bandit theory. And the third step is profit. This is the literal problem statement for this task, right? And step 2 is like spelled out here, which is kind of nice, which is rare. Of course, you can do that a little bit more formally, and let's do that. So the multi-armed bandit problem statement, given a bandit with n arms, each arm I returns a reward, which is sampled from a distribution. Which basically means if I have like Bernoulli arms with a certain probability, I get like 1 token when I pull the arm. And now the goal is I want to maximize the total reward that I get over time. Just basically find a policy that allows me to get as many tokens as possible. Yeah? Okay. And here is such a strategy, the UCB strategy. Does anybody know UCB? Few, okay, cool. UCB stands for upper confident bound, and that is a family of greedy strategies that select the next arm to play to, in the end, maximize the reward. It's not an optimal policy, but it's a very good one, and you can actually prove that it's bounded, that it's like pretty good, basically. Yeah, and it also trades off exploration versus exploitation. What does that mean? If you played a bandit and one arm gave you like, you played it 3 times and you got a coin every time, right? Should you keep playing that one? Or should you like maybe try a different one? Maybe you know, you have to trade off this, want to explore this good one, or do I want to exploit the good one, or do I want to explore a little bit more, hoping that I'll find a better one, right? So this UCB strategy manages this exploration-exploitation trade-off for you. How does it work? UCB basically has 2 components which it uses to determine the next best bandit to play. For one, it uses the past performance. So I played it 5 times, I got a token 5 times, pretty good, right? But it also has this exploration bonus, which basically tells you it's like a trade-off of how many times you played in total versus how many times you played this particular bandit. So if you played like 100 times, like in total, but this one arm you only played once and didn't get a coin, maybe you should play it a little bit more to get some coins, right? Okay, more specifically, there is UCB1. It's a specific UCB strategy which goes something like this. Initially, you play each arm once, just to get some data, basically. And then you play the arm that maximizes this formula. And again, we have 2 parts. We have the past performance mu, the mean reward of a given bandit, plus the second term, which is the square root of 2 log n divided by ni. And ni is the number you played a certain bandit. Looks complicated, but it isn't. Forget the square root, forget the 2, forget the log. What you basically have is n divided by ni. And n is the total number we played, divided by the number we played a certain bandit. So if we played, as I explained before, like 100 rounds in total, but only played this one bandit once, we have 100 divided by 1. It's a big number. So we have a big exploration bonus, basically. But if we played 100 total rounds and played this particular bandit 99 times, we have a big number divided by a big number. It's a small number. We have not really a big exploration bonus, right? That's the idea. That's a bit abstract, right? So let's look at a demo. Okay. The code is not really that important. There are going to be some graphs. But I have 2 Bernoulli arms, basically. One is more likely to give you a coin. The other one is less likely. And I'm going to play 4 rounds in the beginning just to have some data and some more interesting graphs. Then, this is a little bit annoying. I can't really see it from here. You can see the formula. You have the green and the blue. The green is the past performance. That was the mu. Which is just the average of the reward we got, basically. And then we have the square root here, and this is 4 divided by 2. 4 is the total number of rounds we've played, divided by 2. That is the number we played the certain bandit, yeah? So in this case, the first bandit didn't really return too much reward. The second bandit returned quite a bit more reward. And the exploration bonus is the same because we both played them twice, yeah? And now we're going to like play a few rounds and see what happens, basically. You with me so far? Yeah. Okay, cool. So which bandit are we going to play? Who knows? I'll just wait. 1? So you start counting by 0, right? Okay, right. Okay, and what happened? Oh, sorry. We played it, and we got some reward. So the mean reward is the 1. The exploration bonus decreased a little bit because we played it 1 more time. And on the left one, the exploration bonus increased because we didn't play it relatively seen to the other one. Yeah, so we are more likely to explore there. But still, the second bandit looks better. So let's play 1 more round. And we did. We again got some money
The green stayed the same, it's still 1. Here the exploration bonus decreased a little bit, and for the left one the exploration bonus increased. Let's play one more round. Okay, now they're pretty similar. And more specifically, the first one is as a little higher value. So we're going to play the first one, right? We did it, and we didn't get any money. So the green, the past performance decreased, and also the exploration bonus decreased. So you can see that it's like a trade-off here of past performance plus the kind of uncertainty or confidence bound maybe of how often we've played it compared to how often we have played in total, right? I'll just play a little bit longer. But you get the idea. Whenever you get a coin, your performance improves, basically, and your uncertainty decreases. And what you can also see, that the total uncertainty, the bonus, decreases over time. So when we played quite a few rounds, it's less likely that the blue is going to be pretty big. Yeah. I have a feeling that my arrow keys aren't properly working. Okay, I'll just go back. That's fine. Oh yeah, maybe this one, the details aren't very important here, but the bottom line, the pink line, that's a UCB version, and it's pretty much better than most other exploitation strategies, like greedy strategies or simple UCB1 and stuff. They just do quite well, fine. Okay, this is behind this crazy formula, and there are some theoretical justifications of why this is a good formula, but I'm not going to into it. It's still pretty interesting, and you should read the paper. I've linked it in the references. Okay, demo. I already did that. So what can we do now? We have these bandits, and bandits basically give us a ranking of which arm is like a good arm, or the quality of the arms, basically, right? But now we have 100,000 of cars. So should each bandit, each car be one arm? Then initially we would have to play 100,000 arms just to get an idea what kind of cars we like, right? And that is not ideal, right? We simply can't do that actually. Like 100,000 cars, even if you like swiping, you don't want to swipe hundreds of thousands of times, right? So what we do, we use one bandit for a certain feature. And a feature could be something like the brand. So you have one bandit with n arms for n brands. So for Porsche, Volkswagen, BMW, all these things, right? And you have a second bandit for the car body. And the car body, I'm not a car person, could be like something like a SUV or like a mini car or a coupe or something like that. And we have a third bandit for the segment. And the segment is something like a luxury car or a sports car or something like that, right? But in theory, you could use like arbitrary features, right, that you're interested in. And then each bandit here basically creates a ranking for a given feature. It tells me that I like BMWs and that I like mini cars and I don't know, coupes or something like that, right? And this doesn't quite give us the next car that we're going to show, right? But we have a ranking of features that are of interest. And there is a tool which basically doesn't do anything else. That's not true. But Elasticsearch is made for creating rankings from like search queries, from weighted search queries. And we basically use the output of the bandits as input to Elasticsearch. And then Elasticsearch gives us a bunch of cars which match our current interests, like the output of the bandits. Yeah? Cool. We're almost there. We're almost there. I said that in the beginning of the UCB algorithms, you have to play all bandits once, yeah? Play all arms once. But the data is quite biased. Like here we're looking at the brands, and there are lots of Volkswagens, there are quite a few of Peugeots or something like that, and there are very few, I don't know, Porsches, for example, right? So if we just randomly sample from the data that we have, there's a huge popularity bias, and we wouldn't get like good cars that cover the entire car space, right? And we want like good representatives of the data that like cover the entire space. So what did we do? We used some sparse PCA to find the sparse components that optimally reconstruct the data. Whew, that was a lot. So what do? We break down the space into spaces that really nicely represent the data, and afterwards we did like a clustering algorithm, and each centroid of a cluster is like a nice, like a prototypical sample of the data, which like nicely covers the entire space, right? And now we have, let's say, 10 of these samples, 10 of these clusters. And these are the things that we're going to show the user first. And then he swipes, or she swipes, and we get like a good initial guess of the taste of that person. Because, yeah, the representatives are quite different from each other. And then, yeah, you swipe and it actually works. It's cool. Okay, this is how we use bandits, or more generally speaking, like active learning, to work with small data and explore like the taste of the person who's swiping. It was mostly theory, but we had a PyCon, right? So I should have some, or PyData, like a Python conference, so I should at least mention some Python. Of course, we used Python all the way down. Everything is done in Python with the usual suspects. Scikit-learn for all the machine learning part, clustering, segmentation, etc. We have a little REST web server for a Flask web server for the REST API, and the client then, like the Android or iPhone app talks to this web server, and we used Elasticsearch to generate the ranking, and that is also pretty scalable. Like Elasticsearch is made for that. It's super quick. Okay. I still have some time, right? Huh. Okay, conclusion. So what did we learn? And I think what we really learned is what I already told you, that active learning is a great way to think about certain problems where you only have small data. And active learning can really help you to gather data from the humans, or any other process which like could label the data which is expensive. So maybe active learning is something for you, for something you're doing, and you could try it out. It's a super interesting topic. And actually there are very similar topics which are also maybe of interest if you like this, like sequential decision making in general, global optimization, experimental design, Bayesian reinforcement learning. Super interesting and very similar from the setup. Also, there are optimal solutions in the sense like base optimal, and it's called planning and belief space, but mostly it's like too expensive, you can't really do it. And oh yeah, the last point, there is something called hyperband. It's relatively new. It's like a bandit algorithm used for hyperparameter optimization of your machine learning algorithm. And it looks that it's like much better than the usual Bayesian optimization or grid search or whatever you use there. So maybe check it out. Okay, that was my talk. Thanks, our Stefan.
Right, thank you very much. We'll move to questions. Any questions from the audience? Yes, I see hands over there.
Sorry if this is a naive question. A few slides before, first a stage where you did the PCA followed by clustering. And then you chose, if I understood correctly, the centroids of each cluster. Was that more or less correct? My question was, okay, the person labeled those 5. What happens next? What's kind of the second step? This is it, right?
Yes, yes. So this is some pre-processing step we've done before to get like some good samples to cover the space. Then the user swipes and swipes and swipes, and we get information, update the bandits, and after a few batches or like a few swipes, we basically ask Elasticsearch to show us new images. You're completely right. The way I explained it is kind of like backwards. The pre-processing step here is in the end. But I wanted to show how the swiping works first, because without that, you don't really have context for this. Yeah, good question. Thanks.
Another question, right at the back.
Well, if I understand correctly, your approach still only works for binary choice, like, dislike. Is there any way to make that for categorical choice?
So the question was, bandits only work for binary choices? That is correct. And I think in this scenario, it's always for binary choices. From the top of my head, I don't know, but we can have a chat later. I'm very sure that like certain active learning methods can deal with something different. Yeah.
Hi, thanks for an interesting talk.
Thanks.
Bandit theory is more about testing one bandit at a time, but here you're testing 5, 6 bandits minimum at a time with a single picture. So how do you account for that, and how do you cope with it? Have you done simulations trying it?
Yes. So if you're asking me if my inner scientist is happy with the purity of this approach, then it's screaming. But I mean, quite often that's the case, right? Like, does it really make sense? I don't know. It's kind of weird. I agree. But the end result, what the user experience is quite nice. And really, what does a machine learning metric mean for some business case or for some user experience thing? It's you're right. You're right. Yeah.
Thank you for your talk. How would you handle highly dimensional data, where it is not even sample every object? Did you understand me?
No, sorry. Oh, there.
Once again.
Yeah.
How would you handle highly dimensional data, where you could not sample every point?
I mean, this in theory is high-dimensional data. Like a car data point has like lots of dimensions, right? You have the engine, you have the brand, you have the segment, you have the color, you have like all of the extras. What we did here, we picked a few, like car, body, segment, etc. And for each we had a bandit, and that is kind of how we dealt with it. And every time you give like information of like, oh, I like this car, you give us information about, oh, I like this car type, I like this brand, I like this, etc., etc. And we just mixed it up with Elasticsearch, which is maybe not the cleanest solution. But one swipe gives us a lot of information about many dimensions. And we picked 3 to model it here. There was another one somewhere?
Yeah, we have time for about one more question.
There was 20 more questions, yeah?
Okay. Then I directly ask 2. The first one would be, how do you deal with dependency between the variables? Because the individual bandits would be independent of each other. And the second one is, how important is it to go with good centroids in the beginning?
So dependency between the different features. That's a good question. We didn't model it explicitly, but you might imagine that something like a luxury car in general is not a Mini, something like that. So there's a certain overlap which you cover implicitly. Could you do it better? Yes. What was the second part again?
The centroids. How important are the original centroids?
How important are the?
Like the first set.
Yeah, like from this one here, basically, how important are they? We tried a bunch of different approaches and different clustering algorithms and different PCAs and whatnot. It really depends on what user you ask, and it's a user experience thing. They should be sufficiently far apart and cover the space, but you could also think of like other approaches. Maybe you like pick one point at random and then like take one that is maximum far away and another one that is maximum far away from these things. It works, yeah.